Hello, everybody. Hello, Think Inkers around the world. It's a great pleasure to be here. It's been a lot of fun to watch all the names appear in the chat box and so forth. Now, I do hope I have no idea what you're seeing versus what you're hearing. You know, you can see me, but I can't see you. When I was watching Susie and Alan there, I saw them and I heard them, but not at the same time. I could explain this using science. This is due to relativity and the fact that different signals travel to our eyes and to our ears at different rates. Of course, it's complicated in these days of the internet, but it's the same basic principle. That's okay. In this particular example, I'm not going to be using any visual aids or anything like that. It's the words that you hear that will actually matter. And what I thought I would do for today's chat is go into the idea of our preposterous universe, the title of this lecture. Of course, I use this as a title for all sorts of things because it's a fun, catchy phrase, but I don't always explain why we're calling it our preposterous universe. After all, it's the universe, right? How preposterous can it be? And the word preposterous in this case manages to bring up some idea that somehow the universe doesn't make sense to us. The universe is strange or surprising. In one way, that's just perfectly obvious. That's always going to be true. In science, we try our best to understand the universe, but it takes time. We're usually not all the way there. We work toward it. We think we understand more and more, but at any one moment, scientists throughout the world are concentrating on the questions that they don't know the answer to. So the fact that the world surprises us or confuses us is not quite enough. The phrase our preposterous universe indicates that we're in a situation where there are things about our universe that we think we should understand, that we have an expectation for, and yet the universe is not quite doing what we might expect. This is something that really became, for me personally, into focus in the late 1990s. And I want to go through exactly why I'm thinking this and how it puts us in a situation in physics today. It's a very special situation we're in, one that is sort of a crisis/opportunity kind of mode, where there are things we don't understand. Maybe we can be motivated by this lack of understanding to really move forward in some interesting ways. So put yourselves in the frame of mind of me 20 some years ago when I was in graduate school, right? When I was just learning about what our universe was all about. Sadly, it's more than 20 some years ago now, but you know what I mean. The late 1980s, early 1990s was an interesting time in physics, in cosmology, in gravity, but it became much more interesting very rapidly. And the reason why it's interesting is because by that point, we had already basically put together what we call standard models of different areas of physics. And there's all sorts of interesting areas of physics that I'm not an expert on and won't try to talk about, but let me mention three that I think are very relevant here. Cosmology, the study of the whole universe all at once. Particle physics, or what we sometimes call high energy physics, the study of the very, very small, the fundamental constituents of nature. And of course, gravity, right, which Einstein taught us is the curvature of space-time. The point I want to try to make is that in all three of these cases, in cosmology, particle physics, and gravity, we have what we call standard models, by which we mean theories that fit the data, okay? That there is really no, aside from some tiny little quibbles, there's essentially no experiment that cannot be fit into the framework of these theories. That's the good news. The bad news is that we know these theories aren't right. We know these theories are not the final answer to what we're thinking about in terms of how nature works. So that's a very strange situation. Progress in science is usually driven by the fact that we have a theory that predicts one thing, and we go out and measure or do an observation, and it says something else. Here we have a theory that fits all the data we can collect, but we have reasons internal to the theory to think that they're not complete, to think there's something extra going on. So I want to dig into that a little bit and explain why we think that. So let's start with cosmology, okay? This is what I did for a living for much of my career. The study of the universe as a whole. The standard model in cosmology is the Big Bang model, okay? We use the phrase Big Bang, like many phrases in physics, in inconsistent ways. Sometimes the phrase the Big Bang means simply the first moment in the history of the universe, a moment about 14 billion years ago when things were incredibly hot, incredibly dense, and rapidly expanding for the first time. There's already a lot of confusions and myths just about that, okay? Number one, we don't actually know whether that Big Bang was the beginning of the universe or not. Maybe it was, but the equations that we have, which have to do with gravity and general relativity, which we'll get to later, but they're not up to the task. They actually just break down. There's a simple interpretation of those equations that says the universe begins at the Big Bang. It's not a point in space, not an explosion into pre-existing space. It's the first moment of time. It's the day before which there were no other days. But that interpretation might be wrong. It's completely possible that there was time before the Big Bang, that there was some universe, some space and some time that pre-existed what we call the Big Bang. So that's one of the puzzles that we're stuck with. Another is, the other way that we use the phrase the Big Bang is what we call the Big Bang model, which is an entire story of the history of the universe in the last 14 billion years, from the Big Bang to today. The story of a universe that is expanding, cooling, stars and galaxies forming, the universe lighting up and giving us the image that we see in the night sky today. If you go out into that night sky, imagine that you could see the night sky and you had perfect vision, right? So the Hubble Space Telescope was glued to your eyeball. You could see very, very distant objects. You could even measure how fast they're moving away from you. What do you see? You see a universe that is full of galaxies. Galaxies have, of order, 100 billion or a trillion stars per galaxy. And we have, of order, a trillion galaxies in the universe. And they're spread out more or less uniformly. If you run the movie backwards, the universe was hotter, denser, and smoother in the past. So the story of this Big Bang model is one in which gravity, as the universe expands and dilutes, gravity pulls things together. It turns up the contrast knob on the universe. Galaxies form in overdense regions, space empties out in between them, and we go from a relatively smooth plasma to this lumpy universe that we see today. Again, this is a story that fits the data. It fits it spectacularly. We can go all the way back to 1 second after the Big Bang, and we can make empirical predictions, test them against the data, and they come out correct. But you're allowed to ask, why is it like that? Why is the universe smooth? Why did it start out hot and dense? It was actually Roger Penrose, who was one of the real thinkers behind the Big Bang theory back in the 1960s and 70s, who was the first to really emphasize that the Big Bang is a preposterous setup in a very simple way. You can ask yourself, given all these atoms, given all these particles in the universe that you see, if you arrange these particles in different ways, whether or not they're spread out or whether or not they're clumped together, you can say, what would a typical arrangement of this stuff look like, right? What would you expect? If you just took a bunch of particles, there's something like 10 to the 80th atoms in the universe. Okay, so take 10 to the 80th atoms, put them in a bag, arrange them randomly, open the bag and see what they look like, okay? The answer is they don't look anything like the universe that we see. This is a story of entropy. Entropy counts how likely or how disorderly something is. The early universe should have, if we just picked it randomly, be wildly, wildly lumpy, should be inhomogeneous, as cosmologists would say. A universe that is extremely smooth at those early times is extremely, extremely, extremely unlikely. Why is that? Penrose asks this question. Why did the universe start out so special, so preposterous from our point of view? Now, Alan Guth and others suggested an answer to this called the inflationary universe model. If the universe starts out very tiny and dominated by a kind of super dense energy, it can push everything apart while smoothing things out. This is called the inflationary universe scenario or the inflationary paradigm, and it successfully explains why the universe is smooth today, but only at the cost of saying, let's imagine that the universe starts out very smooth and dense and dominated by this crazy kind of energy. And you can do the same calculation that Penrose did, but just plug in crazy amounts of energy that are very small and hot and dense. And it's even lower entropy than the universe we started with. In other words, it's even more finely tuned, special, non-generic. So inflation explains why our universe looks preposterous by saying, well, what if it started out looking even more preposterous? Then it would naturally grow into the universe that we see. So this is not quite sufficient. It's not that inflation is wrong. We don't know whether inflation is right or not, but it's not complete. The story itself undermines itself by not playing by its own rules. All that inflation was supposed to do was tell us why the universe looked natural, and it does so in a very unnatural way. So that's something we have to deal with. And then soon after I was in graduate school, I graduated. We were trying at the time, I was a theoretical physicist, but my friends, some of them were observers and experimenters. And the big task in cosmology was to figure out how much stuff there is in the universe. Like I said, you can see 1 trillion galaxies, that's no problem. But we've known for a long time that the things that we see in the universe are not all there is. There's this stuff called dark matter, this kind of matter that has a gravitational field, so you can tell that it's there. There's no question, in honest cosmology circles, there's no question that dark matter exists. You can have all sorts of different kinds of dark matter. There's a natural idea, well, maybe there's no dark matter, but you just modify gravity, which we'll get to again later. That doesn't work. You can modify gravity if you want, but we have multiple independent lines of evidence that there really is dark matter. Back in 1995, let's say, we were unsure of how much dark matter there was, but we were homing in on the idea that there was not enough. We had an expectation. This theory called inflation predicted a certain total amount of stuff in the universe. And when you took the stuff that we saw, the visible matter, and the stuff that we inferred from its gravity, the dark matter, it added up to about 30% of the universe that was predicted by inflation. This bugged people. It seemed preposterous. Now, we had on the table a way of resolving this problem. You could say that what you see, what you measure by gravity, the ordinary matter, the visible matter, and also the dark matter that collects in galaxies and clusters, maybe that's not all there is, because maybe there's stuff in addition to matter. In particular, maybe empty space itself can carry energy. This is an idea that goes back to Einstein. He called it the cosmological constant. Basically, in every little cubic centimeter of space, if you empty it out so that it's completely empty, there can still be energy there. You would not have detected it by looking inside galaxies and clusters, because it's literally everywhere, spread evenly throughout the universe. There is a problem, though. When the universe expands, ordinary matter and dark matter dilute away. They become less and less dense because the same number of particles is spread out over a larger and larger volume, okay? Whereas if empty space has energy, that doesn't dilute away. The amount of energy in every cubic centimeter of empty space is just a constant number. So in any region of space that's expanding, the energy in particles, the energy in matter, dark matter and ordinary matter, stays the same, but the energy in dark energy, which is what we now call it, the energy in the energy of empty space itself, goes up because it's the same amount per cubic centimeter, and you get more and more cubic centimeters in a region of the universe. That's fine. That's completely okay. Nothing wrong with that. That fits the equations, fits our expectations. The puzzle is this. The amount of dark energy, the amount of energy in every cubic centimeter of space, isn't fixed by any principle that we've ever heard of in physics. It's just a number. It's a number that we don't have any expectation for. Indeed, if you try to make an expectation for it, you predict that it's way, way bigger than what we observe. This is something called the cosmological constant problem. Why is the energy in empty space so much smaller than what we expect? But then there's another problem. If you think that 30% of the universe is matter, dark matter and ordinary matter, and 70% would be dark energy, then these two numbers are changing rapidly with respect to each other, right? Because the amount of dark energy is growing to beat the band as the universe expands, whereas the amount of ordinary energy is not. So if today these numbers are 2 or 3 times different from each other, in the past, the amount of ordinary matter was hugely bigger than the amount of dark energy. Whereas in the future, the amount of dark energy will be hugely bigger than the amount of matter. Why are we born today, right in the time when the universe is interesting and the balance between ordinary matter, and dark energy is approximately equal, roughly speaking? That's what gave birth to this phrase, our preposterous universe. Not that you can't fit the data. You can just say there's this much energy in empty space. You fit the data just fine. But why? It's not at all what we would expect. It seems to say that we live in a special time in the history of the universe. And that is an idea that cosmologists have learned the hard way to try to avoid, try to not make ourselves special in the universe in any way. Okay, that's what we have for cosmology, and those are lingering problems. I mentioned my graduate student friends because one of the people who discovered the fact that there is dark energy is that the fact that the universe is accelerating, which gives us evidence for dark energy, was Brian Schmidt. He was my office mate in graduate school. I made a bet with him that I said we would figure out how much stuff there was in the universe, and he said we would not figure it out 20 years later. Then he went and figured it out, for which he won the Nobel Prize. Brian Schmidt shared the Nobel Prize with Adam Rees and Saul Perlmutter for their 1998 discovery that the universe is accelerating, and Brian is now the Vice Chancellor of Australian National University there down under. So hi, Brian, if you're watching this. Meanwhile, there's particle physics, right? Particle physics underwent this series of revolutions. I mean, basically since the 19-teens, when we started discovering radioactivity and elementary particles, every decade things just changed amazingly, right? And the 1960s in particular were a time when there was this triumph of what we call quantum field theory. The idea that the elementary constituents of nature are not little tiny particles, really. They appear like particles when we look at them, but what they really are fields pervading all of space. When you see a little track in a particle detector that looks like a particle, what quantum field theory is saying is really what you're seeing is a vibration in a quantum field, and that vibration looks particle-like to you because of the magic of quantum mechanics. This paradigm gained acceptance in the 1960s, and in the 1970s we used it to build up what we very imaginatively call the standard model of particle physics, okay? Standard model of particle physics is the most boring name for the most impressive scientific edifice perhaps ever constructed by human beings. We have theories like quantum mechanics, general relativity, statistical mechanics, etc. They're all very nice, very beautiful. What's interesting about the standard model of particle physics is that it's not beautiful. It's a mess. There's all sorts of different particles and fields going around. It's kind of a Rube Goldberg machine. But all of these different pieces play together in such a way as to fit an enormous variety of data. So we have the forces of nature, right? We have electromagnetism, the strong nuclear force, the weak nuclear force. And then we have the kinds of matter particles like electrons and muons, quarks. We have the particles that carry the forces like gluons and photons, the W and Z bosons. And then in the background of everything, we have the Higgs field, which gives mass to electrons and muons and quarks and so forth. And the Higgs field has an interesting place because those other particles we already knew about by the 70s. The Higgs field was posited in the 1960s. And by the 1970s, by the end of the 1970s, I would say, the idea that there was a Higgs field fit the data so well that everybody believed it. But we didn't actually discover it until the year 2012 with the Large Hadron Collider in Geneva. It took an enormous expenditure of effort and ingenuity to actually find that particle. But here's the thing. This was a wonderful, wonderful discovery in 2012 when we finally found the Higgs boson, putting the finishing touches on the standard model of particle physics. There's two interesting things about that fact in particular. One is we all expected it, like I just said. Even though we didn't discover the Higgs boson directly until 2012, everyone, all the major particle physicists by the 1970s thought it was there. In the 1960s and early on in the 1970s, there were a series of experimental discoveries that were quite surprising. You know, the structure of what happens inside protons and neutrons, the number of different families of particles, stuff like that, different symmetries being violated. The 60s and 70s really surprised us in terms of experimental findings in particle physics. But like I said, by the end of the 70s, we had the standard model put into place. We hadn't discovered it all, but we knew what it was. We knew what the predictions were. We predicted what we call the W boson, the Z boson, the top quark, the tau neutrino, the Higgs boson. None of these had been discovered by the late 1970s. But since then, 80s, 90s, 2000s, 2010s, we've found all of them. What we've not done in that time is any experiment that gave us a result that surprised us. The standard model of particle physics was put into place in the 1970s, and all we've been able to do, despite our best efforts, is confirm that it's right. That is weird and bizarre and preposterous. That's almost too good. The standard model shouldn't be that good. It was put together in the 70s. If you have a car from the 70s, you're very, very lucky if it still runs. But here's this incredibly intricate mathematical machinery describing the fundamental forces of nature that works better than ever. That's a little bit puzzling. Here's the other puzzle, that Higgs boson that we have, right? Exactly like the dark energy, exactly like the energy of empty space, you can guess how massive the Higgs boson should be. You can ask yourself, in the context of quantum field theory, you can say, well, if I didn't know any better, what would I expect? Just like you have expectations for what the early universe should be like, expectations for the vacuum energy, you have expectation for the Higgs as well. The answer is that the Higgs boson should be way more massive than it actually is, something like a quadrillion times as massive as it actually is. There's this huge difference between the ultra-high energy scales that we have in gravity and other forces of nature and the energy scale we see in the Higgs boson, or more generally in what we call the weak interactions, which the Higgs bosons participate in. This is called the hierarchy problem. The hierarchy problem is, why is there such a big difference between the mass of the Higgs, which is relatively low, and the ultra-high energy scales of particle physics? It's not what you would expect. But, you know, particle physicists don't just sit around and complain about it. They try to solve it. So people suggested a whole bunch of possible solutions to the hierarchy problem. And guess what? They all, more or less, every one of them, all the most promising ones anyway, predicted that the Large Hadron Collider would find the Higgs boson, but also find a whole bunch of other particles. The Large Hadron Collider has not done that. We have not found any other particles, any new particles besides the Higgs boson. Not yet, anyway. It's always possible that you know, tomorrow we will find some, so don't quote me on this, but as of the last time I checked the internet, we had not found any particles beyond the standard model of particle physics at the Large Hadron Collider. And partly you just say, well, that's too bad, it's unfortunate, but it's worse than that. We really had what we thought were good principled reasons to say that a natural, sensible, non-preposterous theory would predict other new particles at the LHC, and they're not there. Something is going on. What is it? I'm not sure. But let me bring up the third standard model we have, which is gravity, okay? This is our best standard model in some sense because it's the first. It came before the standard cosmological model or the standard model of particle physics. It came from Albert Einstein in 1915. We celebrated the 100th anniversary of general relativity just a little while ago. General relativity is Einstein's idea that space-time, the four-dimensional world in which we live, is not a static, fixed background. It has a life of its own. It's dynamical. It can be warped and curved and bent. And you and I experience those warpings and bendings as the force of gravity. Einstein says that what gravity is the curvature of space-time. And he doesn't just make that poetic assertion. He gives you an equation, which we call Einstein's equation, which tells you exactly how space-time curves in response to matter and energy, okay? It's a beautiful theory. Einstein, you know, he wrote down his equation again in 1915. From that equation, you can predict that there should be something called black holes, that there should be something called gravitational waves, that the black holes should spiral into each other and give off gravitational waves, and we should be able to detect them here on Earth, which we finally just did just a couple years ago at the LIGO Observatory. There's a couple of LIGO observatories, the LIGO Gravitational Wave Observatory. So almost over 100 years pass in between Einstein writing down the equation and us once again showing that this incredibly super high precision prediction of that equation turns out to be true. It's an amazing testimony to the power both of the human mind to come up with the equation, but also of physics. You know, Einstein didn't know about black holes. He didn't know about gravitational waves. He was working on the basis of general principles, and he was able to construct a theory that predicted them. Everything that we've done in astrophysics and cosmology is completely compatible with general relativity, as far as we can tell. That's what makes it a good standard model. Again, zero evidence that general relativity is not correct as far as experiments are concerned. At the same time, we know general relativity is not correct. At least it's not the final answer. There are puzzles in general relativity. One I already mentioned, right? The Big Bang. General relativity predicts infinitely large amounts of energy and curvature of space-time at the Big Bang. The equations themselves break down. You want to try to do better. We don't know how. But more fundamentally, we know that at the deepest levels, the universe obeys the rules of quantum mechanics, right? The universe is not classical. And as different as relativity is from Newtonian physics, it's still in the same spirit. Both special relativity and general relativity live within the paradigm, the framework of classical Newtonian mechanics. Quantum mechanics is something altogether different. Quantum mechanics says that you cannot make predictions with absolute accuracy for the observational outcomes of your experiments. It says that objects do not have exact locations or speeds through the universe, and so forth. All of the other forces of nature, the strong nuclear force, the weak nuclear force, the Higgs boson, electromagnetism, all of these things fit in perfectly well into the quantum mechanical framework. General relativity does not. General relativity does not yet have a perfectly good quantum mechanical theory for which it is the classical limit or the classical approximation. And we've known this for a long time, okay? We've known that general relativity was not really fitting in well with the quantum framework, but it's very hard to actually make progress because there's no experiments we can do. If you think about it, the natural kind of experiment you would want to do to reconcile gravity with quantum mechanics is to have an object which was large enough to create a noticeable gravitational field and small enough to behave quantum mechanically. But to make a big gravitational field, you need something that is at least kilograms to measure its gravitational field, whereas to behave quantum mechanically, you want something the size of an atom or something like that. There is a fundamental discrepancy there. So we're not able to do experiments that teach us how to quantize gravity. What we can do are thought experiments, and that we're really good at. You know, the theoretical physics community is really good at imagining thought experiments. So here's a thought experiment. Take a black hole. A black hole is just so much matter and energy has squeezed into a tiny region of space that gravity has become so strong, light itself cannot escape. So the black hole is that region of space from which light itself cannot escape. Stephen Hawking, who again back in the 60s and 70s, he was friends and collaborators with Roger Penrose. They helped us understand black holes. And Hawking did a brilliant thing. He said, okay, we don't know the quantum mechanical theory of gravity, but what we can do is take a situation in general relativity like a black hole and do quantum mechanics on top of it. In other words, we can imagine the behavior of quantum particles and fields, photons, electrons, neutrinos, and so forth, in the background of a black hole. And what he discovered, to everyone's surprise, circa 1974, was that black holes aren't completely black. They give off radiation. The quantum mechanical evolution of a black hole is not just to sit there, but to gradually evaporate, to disappear. You make a black hole, and it will give off light and matter and energy, and that decreases the energy in the black hole, which therefore shrinks. If you let that happen all the way, then eventually the black hole completely disappears. Here's the problem that raises. This is an awesome thing. Like, you know, it's a great triumph. We haven't, again, observed it directly. It's outside our experimental reach right now, but we have every reason to believe that basic story is correct. And so, but it brings up a thought experiment puzzle. And, you know, I like to say that Hawking's real legacy is not this discovery that black holes evaporate, but the puzzles that that discovery raises for us. The puzzle is this. Take a book, take my books, take something deeply hidden, throw it into a black hole, okay? If you take a book and you destroy it, if you throw it in the water, you burn it or something like that, according to the laws of physics, even though in practice, the information that was in that book is now lost to you. If you burn a book, you can't read it anymore. In principle, if you collected every particle, every photon of light, every little speck of dust from that book, in principle, you could reconstruct what was in the book. Whereas according to Hawking's calculation, if you throw a book into a black hole and let it evaporate, even in principle, the information that was in that book is now gone, has been destroyed by the process of black holes evaporating. And this is something that makes no sense. This is, again, preposterous land. This is something where we don't have experimental evidence that it's wrong, but many of the most cherished principles that physicists like to believe in, conservation of information over time, seem to be violated by this. So this is the closest that we have to an experimental clue about the behavior of quantum gravity, because many physicists, myself included, think that somehow the information does get out of the black hole. We don't know how. We have some ideas. We have some clever ideas, but we're not sure how. So that's the situation we're in. We have a situation in cosmology where we have a standard model, the Big Bang theory that fits all the data. We have a situation in, but we don't know why the conditions near the Big Bang were what they were, nor why the dark energy has the amount it does. We have a situation in particle physics where, again, the standard model fits all the data, but only at the cost of this weirdly unnatural thing, the value of the mass of the Higgs boson. We don't know how to explain that. We thought there would be more particles at the Large Hadron Collider, and there were not. It seems kind of barren. It seems like a desert. And finally, we have the situation of quantum gravity. The black holes evaporating seem to be suggesting the following thing, that somehow there's a mistake in Stephen Hawking's calculation, right? Not a math mistake, like he didn't make a boo-boo, but the assumptions that went into it somehow have to be violated. But the assumptions that went into it are very benign, very vanilla. I already told you that quantum field theory is our best way of thinking about the fundamental laws of nature, and that's basically all that Hawking imagined. That's all that he used, gravity plus quantum field theory. So the suggestion from this is that quantum field theory, despite it being our best theory of nature and able to fit the data, is somehow not right. Somehow, the way to reconcile gravity with quantum mechanics is to move beyond the paradigm of quantum field theory. And maybe that doesn't sound too terrible to you. I mean, quantum field theory sounds like some esoteric technical thing. Probably there's a million different alternatives to it. But really, when you get right down to it, quantum field theory is just the instantiation of the idea that things happen independently at individual locations in space. In other words, when I poke the universe right here, the disturbance that I create ripples out at the speed of light, but from point to point. It ripples out only at the speed of light, not faster. I do not poke the universe here and have suddenly everything change all over the place. If that were to happen, it would be a breakdown of locality. And quantum field theory is the quintessence of locality. It is just a way of taking locality and relativity and putting them into the quantum mechanical framework. So my suggestion, my guess, we're at the end of my time, so I can make crazy guesses, and you can't prove me wrong. You're allowed to ask me about them. The reason why I'm putting all these together, and the reason why I'm telling you about this, is that there's at least a chance that all of these puzzles are related. Right? When we have this situation where there are theories that fit the data well, but we know they're not right, and there's more than one of them. If there's just one of them, we'd be kind of stuck. But if there's multiple theories, maybe there's an idea that solves them all. Now, it would be very nice of me to tell you what that idea is, and I'm not going to do that because I don't know what it is. I have ideas, and I'm not the only one. I'm not even the most important one. There are those of us in the community that have ideas that somehow space is overrated. Space, by which I mean space, this three-dimensional space in which we live, right? Space-time, you could say, if you want to be more 20th century about it. Space-time is overrated. What I mean by that is when we take every other part of the standard model of particle physics, electromagnetism, the strong force, the weak force, the electrons, the quarks, etc., we start with a field that has a basically classical way of being described, and then we quantize it. We apply a set of rules that turn it into a quantum mechanical theory. This is the procedure that has failed for gravity. We have a classical theory, we have general relativity. When we try to apply the rules of quantization to it, they fail. We get the wrong theory. So the idea is maybe we're starting with the wrong starting point. Maybe the quantum theory of gravity is not something we will ever achieve by starting with Einstein's general relativity and quote unquote quantizing it. Maybe we have to start with quantum mechanics itself. In other words, maybe the way to get the unified field theory of everything, I should remove the word field from that, the unified theory of everything is not to quantize gravity at all. but to find gravity within quantum mechanics, to start from a purely quantum mechanical description, not a classical description that we then quantize, but start from the essence of quantum mechanics and show how space-time and the Big Bang and the Higgs boson and electrons and quarks and so forth emerge out of that. Now, it's really easy to say that. It's very hard to do it. Some of us have started this project, and you know what? It will probably fail. I got to be very, very honest with you, because I'm not trying to hype up some crazy speculative idea. What I'm trying to do is give you a flavor of what we're doing in theoretical physics right now. This idea will probably fail because almost every idea will probably fail. That's the nature of the beast. We don't know the right answer yet. We're stuck with this weird situation where we fit the data, but we know we're not right. So we're in a situation where all we can do is speculate about how to go beyond what we currently understand. And it's easy to speculate. It's hard to hit the target. We're playing a game of darts in a room where all the lights are off, where we don't know where the target is. So we hope eventually to hit it, but we're not going to know until we actually do it. So my advice is, there's a lot of people out there now, professionals, amateurs, insiders, and outsiders, trying to understand the fundamental laws of physics. We're not going to do it tomorrow. We're not going to do it in a simple way. It's going to require a lot of work, require a lot of smart people working together. It's going to be gradual, and it will be surprising. It will not be something that's easy to write down. It'll be something where maybe 100 years from now we'll go, yeah, that's obvious. We should have thought of that all along. But at the moment someone actually says it, they're going to be like, no, that's crazy talk. That's preposterous. And that's the trick. That is the progress we want to make. We want to go from an idea and a universe which seems preposterous to ideas and the universe that makes perfect sense to us. Let's hope it happens.
Let's start with the most important question. What was actually the bet? What was the stake that you had with Brian Schmidt?
Well, this was a bet we had when we were both graduate students. Okay, we were poor, and as soon as someone says I was a graduate student, you should presume that poverty follows from that. So we wanted to bet, but we didn't have very high stakes. So what we did is we found a very nice bottle of vintage port, like a small size bottle, not even the full size bottle. And we purchased it with our meager salaries, and we asked one of our senior professors to hide it in his office for the next 20 years. And then we guaranteed, we promised, we wrote down a little contract, 20 years from now, whether or not we would know how much stuff there was in the universe. And then this professor, John Hookra, would act as the referee. But by the time it actually happened, everyone knew that I had won the bet. So it wasn't much refereeing to be done.
Okay. Wonderful. Now, you've mentioned at the start the Big Bang and that hot, dense state, a singularity, if you will. You've also introduced black holes, and of course, famously or infamously containing a singularity within. It's very tempting to draw a connection between the two, and indeed, another great prediction or thought experiment of Hawking was that these could indeed be one and the same, and that perhaps in black holes we have big bangs. And is that an idea that still resonates? Is that still could it be conceivable that we find ourselves actually in a black hole, or does something like inflation just forever destroy that idea?
Well, I think that it's pretty safe to say, despite the temptation, we do not live in a black hole. That's the very short answer to that. And in fact, I can explain why that's the right way to think about it. A black hole is a region of space with the property that if you go in, you can never come out again. Okay, that's what we know. And why can you never go out? Well, once you're inside the black hole, you age into the future until you hit the singularity. The singularity is in your future, and you leave it and you can never come back. Whereas the Big Bang, the singularity is in our past, and everything is leaving it. So the right way to think about the Big Bang is not as a black hole, but as a white hole. The Big Bang is like the time reversal of a black hole. It's still Einstein's equation, it's still the same basic idea, but the dense, hot, high curvature part of the history of the universe is in our past in the Big Bang, whereas it's in our future if you have the bad fortune to fall into a black hole.
Okay, I was always I did enjoy the idea, especially when he was able to start to introduce almost a Darwinian evolution in the sense of numbers. But I guess the key point of that theory was that it at least offered one potential way to find a variety of these numbers, the numbers that you have very successfully, I think, made us clear that they're so preposterous. So why is it that we have these preposterous numbers? Or I guess, what are the ways that tricky theoretical physicists have come about trying to explain them in a more structural manner?
Right. So let me be clear about what I meant by what I just said. We're not inside a black hole now in the aftermath of the Big Bang. But you can also ask, maybe this is what you meant and I just misunderstood. You can ask, could the Big Bang have been created inside a black hole? In other words, when everything falls together to make a black hole and you make a singularity, does it pop out a new universe inside? Plenty of people have had ideas like this. I've had ideas like this. Lee Smolin has had ideas like this. It's a very obvious question to ask. The short answer is nobody has a good scheme of how that's going to actually come about. Okay, we have no reliable theoretical construction which says yes, that is what will happen. Now, Smolin adds a little twist on that idea where he gets this sort of Darwinian natural selection where he says the laws of physics inside this new universe you make are similar to the laws of physics in ours, but they've mutated a little bit. The parameters of physics are a little bit different. So he calls this cosmological natural selection. And of course, you apply what is called the anthropic principle to this. If the laws of physics were incapable of supporting the existence of intelligent life, then you would never know about that universe. As long as eventually you get a universe like ours, that's the kind of universe in which we would live. Now, it's possible, but you can there's a way of getting a large number of universes with slightly different constants of nature in a much easier, better understood way, which is the eternal inflation plus string theory story. So you want to know, does that kind of thing, does the idea that there exists in the multiverse many, many different regions of space that you might want to call universes, where conditions and parameters and laws of physics are very slightly different, does that explain the fine-tunings and the unnaturalness and the preposterousness of the universe that we observe? The answer is you got to do some math. It's not an easy yes or no answer. For the vacuum energy, for the cosmological constant, for the dark energy that makes up about 70% of the universe that we're in right now, it is very plausible that exactly that kind of mechanism would explain the value of the vacuum energy. That would help explain this coincidence problem as to why the amount of energy is approximately the same order of magnitude within these two very different regimes. Sadly, it does not explain why the early universe was very organized and low entropy, and it does not explain why the Higgs boson is so low mass. And it does not explain why the only particle we found at the LHC was the Higgs boson. It does not explain what the dark matter is. So maybe it plays some role, but we really need some bigger, better ideas if we're going to truly claim to have made progress on these issues.
You've raised a few of those mysteries, outstanding questions. How many of them are interlinked? I mean, are we really dealing with n separate problems, or is it, n minus some other number of actually, because one will explain the other will explain the other?
So the problems are all truly independent, in the sense that just knowing that there's a problem in one, if someone told you, I have a solution to, let's say, why the early universe had low entropy, and they say, okay, does that explain the Higgs boson mass or the cosmological constant? And the answer is no, by itself it doesn't. We can hope that there is a common explanation or a common theoretical framework that explains all of them at once. And the fact that we have these several problems and they're all in the character of these fine-tuning naturalness problems suggests that maybe that's a good thing to shoot for, but we don't know. We don't know until we get what the answer is, what the solution is, whether or not they're actually related.
Yeah, okay. I have to also just add, if anyone comes up with a solution to one of those, and in that same email to me also lists that they solve all the others, that I immediately discount that as a theory. But it's good that you probably
exactly that's right. The more grandiose your claim is, the less people should pay attention to it. So let's solve these problems once at a time.
So the idea of an eternal universe, or at least an expanding universe, presents us with another challenge, a coincidence problem, and that is essentially that we are at the very earliest moments of our universe. Essentially, a couple of generations of stars produce enough elements to make up something like us, and apparently here we are to observe it. But stars last for trillions of years. It does strike one as strange that we appear to be here now, not much later. Or have I just misunderstood the anthropic argument in that regard?
Well, no, you exactly captured what a lot of people do say. You might think that the fact that we live 14 billion years after the Big Bang tells us that we live in an old universe. But like you say, stars can last for trillions of years. The universe might plausibly last infinity years toward the future. So in fact, we are absolutely in the very youngest part of the history of the universe. And therefore, if you thought that we were randomly selected from different phases of the history of the universe, you would be very surprised. The question is, should we have ever thought that we are somehow randomly selected? And everyone knows that we're not, right? Like everyone knows that the mass of the Higgs boson or the cosmological constant or the arrangement of particles at early times, none of these are randomly selected. There's not a random number generator that's making all these. What we think, though, is that if we don't know what fixes these numbers, the best we can do is imagine that they're picked randomly. And if the idea that they're picked randomly turns out to be compatible with what we observe, then we say, oh yeah, okay, probably something like that is right. There's no need for further explanation. But when they seem very different than the random numbers, then we try to say, well, I think maybe some different explanation is called for. In the case of the youthfulness of the universe, I'm not sure that any further explanation is called for. Like, if you say, you and I, are we random human beings? Well, we have PhDs in astronomy, right? So, that's very unlikely. Should we be surprised by that? No, because we're not randomly chosen human beings. And I think more or less the same kind of logic works for when we live in the universe. There are more dramatic possibilities, of course, like maybe a few billion years after the Big Bang, some intelligent civilization takes over all the universe and kills everybody else, right? Maybe we're the last generation to survive before the universe becomes monocultural. I don't really know. There's a lot of crazy things you can think, but I think our ability to answer these questions is not really up to snuff right now, so I wouldn't take too seriously any of the specific proposal.
Yeah, that sounds like you're pitching another film plot there, science fiction film plot. I would potentially watch it as well, I have to say. It sounds good. Now, I'm conscious I've only got a few minutes with you, and I really wanted to explore a topic that you often describe on Mindscape, and that is consciousness, or at least this emergence. We have emergence in physics, where we see from simple things come complex phenomena, the unexpected. In the same way, we have the complexity of life and thinking humans indeed today. So is this another thing that we should be surprised about? I mean, the sense that a universe that's essentially has that low entropy start, that we inevitably should find ourselves with complex beings having a discussion like this? Was it all predestined, albeit the path taken was uncertain?
Yeah, no, I would love to know the answer to that question. I don't know the answer to that question. I think that here's what is somewhat safe to say. In order for what you and I think of as intelligent life forms to come into existence, you need two things. One thing is you need this journey from the low entropy past to the high entropy future. That deviation from equilibrium at early times and the relaxation back to it seems to be absolutely crucial for what you and I call life and intelligence and consciousness and all of those things. But there's a second thing that you need. You need that the laws of physics allow for complex structures to come into existence. It's easy to imagine laws of physics that wouldn't seem to allow for any such thing. Imagine that you had a universe where the only particles were photons. It's a very simple universe. Let's say you have gravity too. Gravity and photons, that's all you have. Photons can't come together to form complex structures as far as we know, and we think we know pretty well that they can't do that. So it's not that hard to imagine alternatives to our current physical laws. Maybe even alternatives to our current physical laws that are pretty darn close to our current physical laws. Like if neutrons were a little bit lighter than protons, instead of a little bit heavier than protons, then the world would be nothing but neutrons. there wouldn't be atoms, and these atoms would not come together to form molecules and chemistry and DNA and so forth. So there is a school of thought out there that says if you take the laws of physics that we know about and tweak them a little bit, the possibility of complex life goes away. That complex life is very, very fragile, and it requires very finely tuned conditions. I don't know if that's true or not. It's very difficult for us to judge that because we are so parochial. We are so embedded in the life we actually see, in the laws of physics we actually see, that it's very hard for us to imagine it being otherwise. And therefore, we leap to the conclusion that it couldn't be otherwise, that if there were not atoms as we know them, there would not be life. I don't know if that's true. I think that complex structures can probably arise under a wide variety of circumstances, but I have no idea what that variety is, how to characterize it. I think that's full employment for future generations of scientists.
I'm actually going to start with Suzanthe Heatons, who has this tickles me. Why do we use speed of light when it's more like speed of causality?
Yeah, because light came first. So it's completely historical. This is an excellent question because the point of the question is we have this speed limit built into the universe, which we call the speed of light. It happens to be the speed at which light moves. So it's not wrong to call it the speed of light, in particular the speed of light in vacuum. In air or water or glass, light moves more slowly than that. But the point is that it's more fundamental than just the speed of light. It's also the speed of gravitons, the speed of gravity, for example. And most importantly, it's just the cosmic speed limit. Particles that are not light or gravity, particles that are massive, can move more slowly than the speed of light, but never more rapidly. So influences, again, if I poke the universe right now, the influence from that poking, as far as we know, cannot travel faster than the speed of light. So the fact that it's the speed of causality, the speed of influence propagating through the universe, is indeed the important fact. But historically, before anyone was thinking that way, they were thinking about light, right? In the 1850s, 60s, 70s, Faraday and Maxwell and so forth were able to show that by combining the equations for electric fields and magnetic fields and charged particles, they could figure out what light was, namely that it was a wave in the electromagnetic field and that it traveled at a speed that they could calculate, which is called the speed of light. It was only much later, through Einstein and Poincaré and Minkowski and people like that, that we figured out that the speed of light was this speed of causality. And it is very, very often the case in science that once a name is chosen, the name sticks, even though it's not the best name you could imagine.
Absolutely. Stuart Ralston has asked, why is the speed of light about 300 million meters per second? What determines that speed?
Yeah, the speed of light is 1. As I'm sure you know perfectly well, Alan, it is 1 light year per year.
I hate those units so much.
1 light second per second. The question, so the point is that given that the speed of light is the speed limit, is built into the fabric of space-time, the question is not why is the speed of light 300 million meters per second. The question is why do we use meters and seconds? The speed of light is the speed of light. It's sort of something that supersedes notions of units or anything like that. The reason why we use meters per second is because you're approximately a meter or 2 tall, and if someone says, move your hand, it takes you about a second to move it, right? These are very human length and time scales. And if you want to dig into it, the interesting thing is that a meter is a very short amount of distance, cosmically speaking, and a second is a long period of time. Light moves much more than 1 meter in a second. It moves 300 million meters, right? So the physics question is, why is there this imbalance between the way we measure space and the way we measure time so that the speed of light looks so big to us? And the answer is, in the world in which we live, we're all slowpokes. We all move very slowly compared to the speed of light. Our natural reactions, the way that we think about the world, the speed of our cars and so forth, none of this is anywhere close to the speed of light. So to a very good approximation, we travel through time by a lot whenever we travel through space by a little.
All right, nice. Jonathan Gunnell has asked that he's read that photons experience neither time nor distance. Is that true? And if so, how can they have wavelength?
Good. So there's a whole bunch of things going on in that very short question. One thing is, it's a little bit illegitimate to talk about photons and wavelengths. I know everyone does it, I do it, but wavelengths belong to waves, and particles, photons are particles, right? And the relationship is you have a quantum mechanical electromagnetic wave that exists, and when you observe it, the quantum mechanics kicks in and you see particles. But the thing that is traveling through space is not really a particle, it's a vibration in a wave. That's one fact. The other fact is, guess what? Photons don't experience anything. They're elementary particles. Photons do not have rich inner lives, okay? So there's a technical fact that we translate into loose natural language. The technical fact is that there is a way of measuring distances in space-time and intervals. So intervals of time, distances in space. And the way that works out in space-time is that the curve along which a photon travels has zero space-time interval, okay? So if you could talk about it experiencing time, it would experience zero time. And when you say to a physicist a photon experiences zero time, they know what you mean, okay? But it's not like there's a conscious photon and it just experiences the whole universe all at the same time. It's just not like that. It's just that, the photon moves from our perspective, but there's no such thing as a clock carried by a photon. That clock would not move. It would not actually be any different from one moment to another.
There's the idea that as you go faster, your time ticks more slowly relative to an observer at rest. And so I think that's where the experiential question comes in, because we can imagine ourselves traveling off to Alpha Centauri with great speed, and the journey feels like it was only a few days if we were able to go fast enough, right?
Yeah, I try to be careful about this. I don't always succeed. I do not like to talk about clocks or time flowing at different rates, because from your perspective, on that journey to Alpha Centauri, every time you look at your clock, it's ticking at 1 second per second. Okay? Right. The time that you feel never feels like it's speeding up or slowing down. As you said correctly, when you compare it somehow to what is observed by someone who is moving in a different way through the universe, they can have experienced a different amount of time. And the rule is that the people who stay behind and don't move experience the most time between any two events. So it's almost irresistible to say that time slows down when you move close to the speed of light. But you know that Einstein taught you there's no such thing in any absolute sense as moving close to the speed of light. All speeds are created equal in relativity. The correct thing to say is that the journey you take by zooming out to Alpha Centauri and zooming back will have less total duration as measured by a watch than one where you just stay home on Earth.
Well, I couldn't resist the temptation to use the shortened analogy. All right, we have a lot of questions on gravity. I'm going to, excuse me all, there are being so many have come through. Okay. Oh, good. Justin Freeman has asked, let's get into gravity. Why is it that the mass above which a neutron star causes itself to collapse into a singularity is also the mass at which an event horizon is created? If I asked that right, why is the mass above?
Yeah. Okay. No, I mean, I think I get what is being asked here. There's actually, there's both general relativity, which is the theory of gravity that Einstein invented that is just universal. It applies to all things. They all feel gravity in the same way. But then there are specifics about the kind of matter that exists in the universe. So, the Earth maintains its shape. It does not collapse to a singularity because there's pressure inside from the materials that are inside the core of the Earth. The sun maintains its size for a different reason, but because there is nuclear burning going on that creates heat and creates a different kind of pressure. And as conditions change, that may or may not change. The Earth could last a very long time. The sun will eventually give out and shrink, right? And then to say what happens when it shrinks, you need to know details. You need to know the details of what it's made out of. The sun will shrink down to something called a brown dwarf, right, where it's sort of given off all of its nuclear fuel, has stopped burning. And depending on details, it could become a white dwarf, which is the most dense that ordinary matter can come without going through some dramatic phase transition. A white dwarf is held up by the pressure of the electrons inside the white dwarf. Electrons have a certain size. And remember, this quantum mechanical rule, the more massive something is, the smaller it is. So electrons are what keep white dwarfs at their size because they're the least massive constituents of atoms. The neutrons and the protons are more massive and then therefore can be fit into a smaller region. So it's just a feature of the laws of physics that the white dwarf is not the final stage, because you can take that electron and the proton that is also in the nucleus of the atom and combine them to make neutrons. So there's a way of converting protons and electrons into neutrons, making nothing but these heavier particles, which therefore can be squeezed into a smaller star. And so that's the neutron star. And the question is there something you can do to a neutron star that can make it smaller without going all the way to a black hole? The answer is we don't know. There are people who have suggested that there are weird nuclear states of matter that are literally called strange stars, where it would be smaller than a neutron star, but not that much smaller. It turns out that numerically, neutron stars are pretty close to the size of their event horizon, so there's not a lot of wiggle room. The size of the event horizon has nothing to do with details of matter and neutrons and protons. All you need to know is how much mass and how much size. It comes right from general relativity. So it is possible there are ways to arrange the elementary particles of nature into a stable configuration that is smaller than a neutron star but bigger than a black hole, but that's still very speculative and we don't know for sure. In fact, I haven't actually followed the people studying that for a living. Maybe they do know for sure by now. When I was young, they actually thought about that possibility.
No, I think cutting edge is still, there's one or two objects that seem a bit suspiciously large, basically, but no, we're pretty sure we haven't seen a definite clear-cut example of a strange star, a quark star. Okay, so we have some questions about the far future, and actually I'll start with Matthew Deans, who has read your 2017 paper, Why Boltzmann Brains Are Bad. Do you still say they are bad? And that's going to take us onto a lovely journey of the far future, of course.
Yes, I still think that they're bad. I am less, as they say in that paper, I already had the opinion on that paper that Boltzmann brains appear less frequently than you might worry about. But when they do appear, they're bad. So for those of you out there who don't read all of my papers, a Boltzmann brain is the idea that if you have some fluctuating collection of matter, so the standard thought experiment example is just a box of gas with a bunch of molecules bumping into each other, but a box of gas that is really, really, really big, and you let it fluctuate literally forever. Most of the time, it's in what we call thermal equilibrium. It's in a high entropy state. It's very smooth and spread out. Nothing interesting is going on. But just through the magic of random fluctuations, it will occasionally take on interesting shapes. They are individually unlikely, but what that means is it's unlikely they appear at any one moment, but you have an infinite number of moments to wait. So eventually they will all appear. And it includes, in the set of things that appear, a brain or a whole person, or for that matter, if the box is big enough, a solar system or a galaxy. So we think that people like you and I evolved more or less respectably over the course of 14 billion years since the Big Bang, with entropy going up the whole way. But it's possible to imagine life forms that simply fluctuate into existence from a high entropy state into just a single brain, just a brain that is alive enough to look around and go, thermal equilibrium, and then it dies, okay? And if you imagined that things like that happened, remember, if the universe is eternal, they can happen infinitely often, and there'd be infinitely more of them than there are of us. So that would be bad for these anthropic principle reasons that we worried about before. So I absolutely think that would be bad, and we can go into details about how bad it would be or whether you can wriggle out of it. But the point is, What I no longer think is that the universe is like a box of gas. I no longer think that, and I already had changed my mind again by 2017, but I used to think that if you wait long enough, the universe empties out. But because of this dark energy, because of this cosmological constant, there will always be some slow churning of the quantum mechanical fields in the universe that can be thought of as random fluctuations. I think that was a mistake. I think I've changed my mind about that. I think it's better to think of the universe as evolving toward some quantum mechanical state where everything is just static, everything is just quiescent. So an eternal box of gas would really have a Boltzmann brain problem, but I actually don't think that the quantum mechanical universe is very much like an eternal box of gas.
Yeah, so that actually takes us to a question from Paul Hess, which you have partly answered now. But if the universe eventually expands to infinity, wouldn't that just be flat nothingness? So information would not be conserved; it would just all be gone. So, but he's also partly answered, I think, the Boltzmann brain argument as well.
Yeah, but it's a good question because we think that information is still conserved. That doesn't mean it's accessible to us. Like, we didn't worry about conservation of information before Hawking taught us that black holes evaporate. It could still have been true that I can take a book and throw it into a black hole and it's lost to me, it's behind the event horizon. But we didn't worry about that because we didn't think that the information was destroyed, it was just taken from me, okay? It was stolen, it was hidden, it was inaccessible. Cosmologically, the same thing can happen. Cosmologically, we have a horizon around us. We're in the middle of a horizon rather than outside. Things that move far enough away from us can be lost to us forever, cosmologically. And in that case, the information that is accessible to us is not conserved, but we never really thought that it should be. So that's not really a big worry.
All right. Okay. Now we have various questions about the speed of light came up, about can you travel faster than the speed of light? And Nathaniel Hall has asked if light travels slower through different substances, does that mean communication maximums are also slower? Yes. So
no, it does.
I guess
it depends on what you mean in principle or in practice, right? In practice, you could always communicate using gravitational waves, and they would still move at the speed of light.
Indeed. Well, actually, just out of interest, I mean, how creative can you get in terms of communication? Not to steal another of your perhaps film plots for another Hollywood blockbuster, but fundamentally, how can we communicate, right? I mean, we talk about neutrinos, there's gravitational waves, there's light. Is that it? Do we run out of other options meaningfully?
Well, you can send someone a letter. You can use protons and neutrons and electrons, right?
Yeah. Can you actually do that today? I don't know. Ozpost has not been great.
Yeah, it might be difficult. Sorry about that. Yeah.
But the idea of communication is central to your ideas of perhaps this universal theory, and really the transfer of information. So it's becoming an ever more important fundamental field, just the basic principle of information, what we all mean by communicating.
Yeah, I think that the way that I like to think about it is the following. Think about energy. The concept of energy is enormously useful, obviously, in physics and how we think about things. And there's different types of energy, and they transform between each other and so forth. Where would we be as physicists without the concept of energy? But energy is not a thing. It's not a substance. It's not like, oh, here's some energy, right? Energy is a property. You say, here's an object, and it has a property of having a certain amount of energy. Here is a field or a wave, and it has a certain amount of energy. And what we're realizing is that information is exactly the same way. Information is not something that exists by itself. It's a property of physical stuff in the universe. But thinking of the physical stuff in the universe in information terms is enormously useful, is really, really helpful when it comes to understanding how things go, such as how black holes evaporate, how quantum computers work, maybe even how space-time itself comes to be.
So you don't subscribe to the idea that we actually have a bigger universe, which is a mathematical universe? Obviously, if anyone's listened to Mindscape podcast recently, you would have heard a fantastic episode on this. But were you convinced in that idea that information is more real, more fundamental in some way than what we physically experience?
Nah, that's crazy talk.
Max Tegmark, I hope you're watching.
Should buy Max's book. Max wrote a very good book, but I don't believe a word of it. I mean, I believe most of the words in it, but I do not believe the fundamental deep conclusion there. No, I think that there's a big difference between worlds that exist and worlds that don't. They don't all exist.
Okay. Peter Klein has asked, is Sheldon correct in thinking that string theory will not lead anywhere?
I think that string theory is already led somewhere. So no, Sheldon is not correct. If you want to know, is string theory the correct theory of gravity and space-time? That I don't know. String theory has a lot going for it. It's one of these things, once you get into it, it really is remarkable how many good things come out of string theory. Like if you're a theoretical physicist and you spend your time writing down new ideas for different ways that the fundamental stuff of reality can come together, you quickly realize that most of your ideas crash and burn very, very quickly. They run into problems with either data or internal consistency. Whereas string theory, was meant in the 1960s to try to explain features of strongly interacting particles, right, of protons and neutrons and their cousins. And it didn't quite work for that, but only because it kept predicting gravity and other forces of nature, things that it wasn't even supposed to be predicting. And that sort of paradigm has continued. That tendency of string theory to be better than we are has really continued. And this is why people get very enthusiastic about it. At the same time, there's zero experimental evidence that it's actually on the right track. And I think it's fair to complain that an increasing number of professional string theorists are doing string theory without really trying to connect it to actual physics, without trying to connect it to the rest of the world and to the data to explain what we see. And so I have mixed feelings about string theory. I think that a lot of its critics just don't understand it. They don't understand the reason why the people who do it do it. But on the other hand, I also think there's legitimate criticisms to be made and legitimate worries to have about whether or not it will still be considered important 20 or 50 years from now.
Wow, all right, some fighting words there for any string theorists on the line. Look, what it's worth, very impressive. It's no doubt it is an impressive theory, but I would be very worried about the great people I have seen delve into string theory and perhaps not follow a career in trying to discover high temperature superconductors, right, or other fascinating physics problems that their incredible minds would have perhaps solved by now. So that's my personal take on it. I've just seen some great people go down a black hole, basically. And that was my segue to David Barvis' question. How feasible is it to use black holes as a means to study that intersection of quantum mechanics and general relativity, essentially to get to a quantum gravity?
Well, we've been very good at using black holes as thought experiments, as I mentioned. What we'd like to do is to use black holes as actual experiments, right? To actually collect data from real-world black holes. We know that the black holes are out there. Astronomers have done a very good job in giving us information that makes us 100%, nothing's ever 100%, but super duper confident that black holes are real in the universe, whether it's the X-rays from accretion disks or the gravitational waves or whatever. So far, all of the data that we've gotten from black holes is completely 100% compatible with general relativity. There's no hint of anything beyond general relativity and need to quantize gravity to explain them or anything like that. But we shouldn't have expected otherwise. The kinds of data we have are kind of crude when it comes to asking what exactly is the geometry of space-time near the event horizon of a black hole, for example. What we would like to do, what we hope to do, is to improve the precision of that data. And we have a bunch of experiments coming online to do it. Very famously, there's the Event Horizon Telescope, which took that famous orange circle picture that is actually a picture of a black hole. It's a big fuzzy blob. You don't get a lot of details from it, but it gives you the hint that maybe details are out there to be gotten if we raise our game a little bit there. And likewise, the gravitational wave community has, collected data that convinces us that black holes are there and spiraling together. But there are huge improvements that could be made. If we put a black hole, gravitational wave observatory in space, we will, in principle, be able to map out the space-time geometry near a black hole to incredible precision. And then we might actually learn something about quantum gravity. Maybe not. In fact, probably if you wanted to bet at even money, you should say probably not, because classical general relativity still probably works. But we could. It's a non-trivial chance. It's certainly better than any chance we have of just doing good old tabletop experiments here on Earth.
All right. Look, I think those ideas of the ring down phase, right? So you get the collision of the black holes. That's I'm a part of the Center of Excellence for Gravitational Wave Discovery, OSGRAV. We get very excited about that bit of the in-spiral, or sorry, the collision, because you have a chance to reveal perhaps something you didn't predict from GR. Spoiler so far, no, it looks like GR, but we live in hope, right? New detectors all the time. Justin O'Brien has asked, okay, I can see this opening up a black hole. We have 10 minutes. Are we any closer to being able to test the falsifiability of any quantum theories, or maybe let's just spend a few minutes, indulge one of your favorite topics, and indeed the subject of the book just across my shoulder, quantum mechanics. Just essentially, where are we at with the fundamental understanding of quantum mechanics?
Sure. Quantum mechanics, a fun thing to think about. I wrote a book about it. I encourage everyone to read. My favorite theory of quantum mechanics is the many worlds interpretation of quantum mechanics. And the crucial thing here, all we need for this particular question, is the fact that many worlds is not a theory that you invent by saying, well, what if there's a bunch of worlds, okay? It's a theory you invent by saying there's a quantum mechanical wave function that describes quantum systems, and that wave function evolves according to an equation, the Schrödinger equation. And that's it. Every other version of quantum mechanics either says, in addition to the wave function, there's other stuff, or they say, in addition to the Schrödinger equation, there's other ways the wave function can evolve. So you want to falsify this theory, it's the simplest thing in the world. Just find evidence for either other variables other than the wave function, or evidence for evolution of quantum systems that violates the Schrödinger equation. And guess what? Experiments are being done to do exactly this. So the many worlds interpretation of quantum mechanics is the most falsifiable theory ever invented, and we're trying to falsify it right now. My prediction is it will not be falsified because it is not false.
All right. Okay, Justin, there you go. The idea of the many worlds paradigm, it is a more extraordinary outcome, let's just put it that way, of as you say, a very simple interpretation of quantum mechanics, the most conservative interpretation. Very quickly, these multiple worlds, do they exist? Where are they? What does it feel like when a many worlds, sorry, is actually created?
Yeah, we don't know how many there are. They're coming into existence all the time. Basically, again, the many worlds theory is extremely quantitative and precise about what happens. Namely, systems obey the Schrödinger equation. So you can solve that equation for whatever initial conditions you want. And what happens is when a small quantum system that is in what we call a superposition of different possibilities, like an electron, rather than just spinning clockwise or counterclockwise, can be in a superposition of doing both at once, until that electron becomes entangled with the rest of the world. Entanglement is this crucial feature of quantum mechanics where the state of one part of the world can be entangled, can be interacting and associated with, correlated with, the state of another part of the world. So if the electron is just by itself, isolated, not interacting, not entangled, then it's in a superposition. But as soon as it gets entangled by measuring it or something like that, that's when the universe branches. That's when we have multiple copies, one of which says, oh, the electron was spinning clockwise. In the other one, the electron was spinning counterclockwise. So this is happening all the time. How many total branches we can have, we have no idea. It could be an infinite number, it could be a smooth continuum of possibilities, or it could be a number that is finite but just really, really big. What we cannot do is go visit. They're not located next door, they're not located anywhere, because what does it mean to be located somewhere? It means that there is something called space, and you have a position, a location in space. But space exists within the worlds, within the different branches of the wave function. The branches do not exist within space. Space is much less important than the wave function of the universe.
All right, that was a little teaser for anyone out there, a little taster of this, something deeply hidden. As I said, this book on my shoulder. Okay, in a real intellectual workout, we're going to jump back because we keep getting questions. So Eliza Pacciano has asked back to that idea that a black hole in one universe is a white hole in another, right? Or if that's what we had as our Big Bang, for example. So in that case, do we see information pass from one universe to the other and without loss?
Yeah, I mean, the only honest answer to any question like that is we have no idea, right? We don't know what happens or what would happen when something collapsed to a black hole in one universe and then spat out a Big Bang on the other side. We can babble about it. We can make statements like what we think should happen, but we don't actually know. I suspect that some kinds of information should be able to be passed from one universe to another if universes actually do pinch off in that particular cosmological way. That's my guess. But don't take my word for it and don't think we know. These are just ideas well beyond what we have any confidence in when we talk about them.
So where do you think we're going to go? You mentioned it took a century to essentially definitively test the most extreme of the predictions of Einstein, for example. So a century from now, do we look back and turns out it wasn't a dream, it was something weirder, or quantum mechanics when we treated its take on space and time truly and deeply, and then built an entire physics framework up? Is that how we find out this grand unified theory, or are we still searching in the dark?
Yeah, well, who knows? I mean, again, if I'm being honest, this is not something about which it is in any way possible to reliably predict the rate of future progress. Let me give you two scenarios. Here, first, the pessimistic scenario is the following. Isaac Newton came up with Newtonian classical mechanics in the 1600s, and that was an amazing thing. Like, that was really revolutionary and still what we teach our first-year students today. The 1700s, there was progress, but it was sort of, not that much progress. And then things ramped up. In the 1800s, we had electromagnetism, we had the first hints of radioactivity and things like that. We had statistical mechanics and thermodynamics and entropy. It was really a fun time in physics. And then there was the first 30 or so years of the 20th century, which was just this amazing historical time where we invented special relativity and real, particle physics and nuclear physics and general relativity and quantum mechanics and quantum field theory all in rapid succession, and the Big Bang, right? The expansion of the universe, all in the 1920s. And then we did pretty well in the decades after then, but the second half of the 20th century, the second 2/3, was unmistakably slower than that first 30 years, which was absolutely singular in human history. And maybe we just experienced a rise to a peak, and now we're in the aftermath, which will take a long time, and progress in physics will become slower because the low-hanging fruit has been picked. That is absolutely plausible, and maybe unifying gravity and quantum mechanics won't happen in the next 100 years. I don't know. Maybe it won't happen in the next 1,000 years. But that's the pessimistic point of view. The optimistic point of view is the following. We have these ways in which our current view of the world seems preposterous to us. They're not direct contradictions between experiment and theory, so they're not quite as directly helpful as a good old experiment would be. But they maybe, this is the optimistic point of view, maybe they're reaching a crisis point. Maybe it's the point now where we've exhausted the easy ideas, the easy suggestions to how to fix these things, and we have to think more deeply. And maybe an increasing number of people will begin to think more deeply, to think about the foundations of quantum mechanics, the nature of space-time at a fundamental level, the principles of locality and the ways in which it's violated. And maybe 5 or 10 years from now, this will all be put together in some brilliant new structure. And we realize, oh my goodness, like everything we thought about quantum mechanics and gravity and field theory is just an approximation to some much deeper and more beautiful structure that solves all of our problems.